There are two systems of units we'll encounter as we solve problems in statics: English or US customary units and metric or SI units. Because our governing equation, F equals ma, is inferred from observation and not derived from something more fundamental, one of the four physical quantities implied by F equals ma must be derived from the other three. In terms of units, the equation is force equals mass times acceleration, which has units of length, over time squared. As an aside, when I'm referring to units, I will frequently put them in square brackets like this. Note that the units of acceleration have been explicitly represented as length over unit time squared. In the case of the English or US customary system, length, time, and force are the fundamental units, and mass is the derived unit. We define one slug to be the mass that experiences an acceleration of 1 foot per second squared when subjected to a force of 1 pound. In the SI system, mass, length, and time are the fundamental units, and force is the derived unit. We define 1 Newton as the force required to accelerate a 1 kilogram mass to 1 meter per second squared. It is an unfortunate fact that many people use weight and mass interchangeably. As mentioned earlier, in addition to being different physical quantities, one is a vector and one is a scalar. If you've ever watched a weightlifting competition, you may have heard a sports announcer refer to a weight in terms of kilograms, as in, he's now going to try to clean and jerk a 100 kilogram weight. But 100 kilograms is a mass, and a 100 kilogram mass is the same on Earth as it is on Mars, even though the weight experienced by that same 100 kilogram mass would be different on Earth than it is on Mars. It would be more accurate to say that a 100 kilogram mass experiences a weight on the Earth's surface equivalent to 220 pounds, but that's a mouthful likely to be quickly forgotten by viewers. If you are an aspiring engineer or physical scientist, this distinction between mass and weight is important, and we will absolutely impose point deductions on exam problems for confusing the two. Weight is a force and a vector and has units of either pounds or newtons. Mass is a scalar and has units of either slugs or kilograms. The relationship between them on Earth will be described shortly. As part of your calculations, you may occasionally have to perform unit conversions. A few common ones are listed here. Perhaps the only quantity you haven't previously seen is the kip, an unfortunate contraction of kilo-pound that refers to a 1,000 pound load. You are not required to commit these conversion factors to memory, although there are a few numbers you'll see so often that you may want to memorize them anyway. As an example of a typical unit conversion, we convert a speed in SI units to one in US customary units. Multiplying any physical entity by unity, that is, a dimensionless factor of 1, doesn't change that entity. We can think of conversion factors as dimensionless factors of 1 that permit us to change an entity from one system of units to another. In the present case, the ratio of 1 foot to 0.3048 meters is a dimensionless factor of 1, and we multiply the entity in such a way that the units cancel in numerator and denominator. This gives us, in the present example, a speed of 32.808 feet per second. As an aside, we should say something here about the appropriate number of significant figures in calculations. Your Connect homework assignments count answers as correct if your numbers fall within plus or minus 2% of Connect's actual value. On that basis, 3 significant figures is just fine as an answer, and a speed reported in this case as 32.8 feet per second is just as good as the value of 32.808 feet per second. If you like, you can use 4 significant figures and report the speed as 32.81 feet per second. You will never have an answer marked as incorrect if you are doing the problem correctly and reporting answers to 3 or 4 significant figures. If you find yourself in homework or exams writing down all the numbers your calculator gives you, then you're just wasting time. With respect to significant figures, think 3 or 4, no more. There are a few applications in physical sciences where it actually is important to retain large numbers of significant figures, but none of those special cases occurs in statics. One other issue about the description of physical quantities is that we will sometimes run across very large and very small numbers in our system of units. In these cases, the following set of prefixes is useful in representing numerical values in more compact fashion. Table 1.3 of your text lists a more extensive set of prefixes, but most engineering applications are covered by this range, from billion, giga, to billionth, nano. As an example, the stiffness of common structural materials, steel, aluminum, concrete, or wood, is measured by something called an elastic modulus. In SI units, this stiffness typically has a value in billions of Newton per meter squared, or billions of Pascal. We define 1 Pascal to be equal to 1 Newton per meter squared. And for example, the elastic modulus of steel is 200 billion Pascal, 200 billion Newton per meter squared. So often when we're reporting these stiffnesses in SI units, we report them just as 200 GPa, 200 gigapascals, or 200 times 10 to the 9th Newton per meter squared. As an example, let's perform the following unit conversions. The first one, we have a weight density of 175 pounds per cubic feet. We'll multiply that by 4.448 newtons per pound, and then times 1 foot per 0.3048 meters. And because we've got cubic feet with our original quantity, we've got to cube this so that feet cubed here cancel feet cubed here, pounds cancels pounds, and this will give us a weight density in newtons per cubic meter. If we multiply that out, we get 2.75 times 10 to the 4th newtons per meter cubed. And if we want to use one of our prefixes, we'll use the kilo prefix, which is 10 to the 3rd. This is equal to 27.5 kilonewtons per cubic meter. Our second example gives us a speed in feet per hour. We could take 6 feet per hour and multiply that by 0.3048 meters per foot times 1 hour per 3,600 seconds, Again, we multiply this in such a way that the units cancel in numerator and denominator, and we get a speed in meters per second. In this case, that turns out to be equal to 5.08 times 10 to the minus 4 meters per second. And we can then use our millimeter prefix to write that as 0.508 millimeters per second. Finally, we have a torque in kilonewton meters that we want to convert to US customary units. So we'll write this as 1.13, it's in kilonewton meters, so that's times 10 to the third Newton meters. We'll multiply that by 1 pound per 4.448 newtons, and 1 foot per 0.3048 meters. Again, the units cancel, numerator and denominator, and we're going to get a torque in foot-pounds, and that number turns out to be 833 foot-pounds. Finally, we close this lecture with a few remarks about gravity and weight. It is important to understand that this law of gravitational attraction was inferred from observation. Newton found by experiment that the strength of gravitational attraction was proportional to the masses of the interacting particles and inversely proportional to the square of the distance between them. For this reason, the gravitational constant big G has odd units and exists to convert the observed dependencies into a force. You may also note that it has a very small numerical value, and this reflects the fact that gravitational attraction is the very weakest of the fundamental forces in nature. It should also be noted that this expression is valid for particles, where the distance between them is unambiguous. In the figure, we have bodies characterized by radii r1 and r2 that are not small compared to the distance between their centers, r. If we are instead trying to express gravitational attraction between bodies, as shown in this figure, what do we use for r in Newton's expression? It turns out that if the bodies in question are spherical and homogeneous, that is, they have constant mass density, then it is possible to use Newton's law of gravitational attraction as long as the distance r in the expression is the distance between the centers of the bodies as shown in the figure. Most of our applications of gravitational attraction will involve man-made bodies near the surface of the Earth. Even large man-made bodies are minuscule compared to the radius of the Earth, so the distance between centers in this case simply defaults to the radius of the Earth. Defining weight as the force magnitude exerted on the man-made body by the Earth, we can rearrange our expression for the force so that it becomes the body's mass times a collection of constants that includes big G, the mass of the Earth, and the radius of the Earth. This parameter involves the product and division of very large and very small numbers, but fortunately, when we calculated out its result, the numerical value comes out to be quite reasonable in either English or SI units. There are few numbers you should commit to memory, but one of them is the gravitational acceleration, or little g, defined here. Little g turns out to be either 32.2 feet per second squared or 9.81 meters per second squared, and the weight of a body is calculated from its mass as weight equals m times g. Returning for a moment to an earlier comment about units and the mistaken confusion of mass and weight, consider again a weightlifter trying to hoist a mass of 100 kilograms. Using our value of little g, as well as an appropriate conversion factor, we could say accurately that the 100 kilogram mass amounts to a weight of 100 kilograms times 9.81 meters per second squared equals 981 newtons. And then convert that to pounds with our conversion factor of 1 pound per 4.448 newtons. That gives us a value of 220.5 pounds. And we can then say that a 100 kilogram mass is equivalent to a weight of approximately 220 pounds on Earth. As a final example, we'll consider this problem involving two small spheres placed adjacent to one another on the Earth's surface. There will be a force of mutual attraction between them that will be very small compared to the force exerted on either one by the Earth, but we'd like to compare the relative size of those two forces. We'll begin by calculating the weight of one of the spheres. One of the things to notice here is that we have a mixed set of units in the problem statements. The spheres are given as having a diameter of 100 millimeters, but they're given a weight density, or so-called specific weight, in English units of pounds per cubic inch. So we're going to have to go back and forth between the two systems of units in order to get the answers we're seeking. So the first thing we'll note here, we're looking for weight, which is mass times little g. And the problem statement gives us a weight density. That is, it gives us a weight per unit volume. I could write the weight as the weight per unit volume times the volume. This value here is what's presented as gamma, or the specific weight, in the problem statement. So we could write this for a single sphere as gamma times the volume of the sphere, which is 4/3 pi times the radius of the sphere cubed. Now, because we have mixed units, we're going to have to convert one of these to the same units as the other, and I will choose to convert SI units to English units to start with respect to the radius. So the radius is 50 millimeters. Right, that is 50 times 10 to the minus third meters times 1 foot per 0.3048 meters, and that gives me a radius of 0.164 feet. The weight then is equal to gamma, which is 0.284 pounds per inches cubed times 12 inches per foot, and we have to cube that so that the inches cubed cancels here and here, multiplied by 4/3 pi times 0.164 feet cubed. That will give us a weight in pounds, and that number turns out to be equal to 9.067 pounds. We could then convert that into a weight in newtons by multiplying by 4.448 newtons per pound, and that gives us a weight of 40.33 newtons. Now, in order to do the second part of the calculation, where we find the force of mutual attraction between these two spheres, we need to know their masses. So we will calculate the mass as the weight divided by little g, 40.33 newtons. And remember that a newton is a kilogram meter per second squared. So dividing that by 9.81 meters per second squared cancel, and we get a mass of 4.11 kilograms. Now, to calculate the force of mutual attraction, we're going to need the distance between centers, and here with these two spheres placed next to each other, the distance between centers is twice the radius or equal to the diameter of one of these spheres, which is 100 millimeters. So we'll use that in our calculation for the force of mutual attraction. We have F equals our big G, m1, m2 over r squared. Again, here, m1 is equal to m2 is equal to 4.11 kilograms, and the r, the distance between centers, is 100 millimeters. So in this case, our force of mutual attraction is big G, which is 66.73 times 10 to the minus 12th, with units of meters cubed per kilogram second squared, times 4.11 kilograms squared over 0.1 meters squared. And we'll notice here that the kilogram cancels out the kilogram squared here. We'll have units of, when we're done, we'll have units of kilograms from that, and then we have a meter cubed in the numerator and a meter squared in the denominator, which will give us a net meter, and we've got second squared down here at the bottom, so the units of this are in fact going to turn out to be units of newtons. So when we calculate all that out, we get 1.13 times 10 to the minus 7th newtons. Not surprisingly, that's a very small number, and that we could write that as 0.113 micronewtons, which is obviously much less than the weight. So the force of mutual attraction between these two spheres is a very small number compared to the force exerted by the Earth on one of the spheres.